Greetings, everyone. Thank you for having you for the second time. Really appreciate this spirit of sharing knowledge and your hot enthusiasm for the topics. Today, it's all about you guys. So today you will share your nice topics with us. So this will be a very good opportunity for all of us to listen to each other, and this is maybe the target of this course. Is sharing knowledge, not like one side sharing knowledge. It's like sharing knowledge from all of us. So I appreciate your sharing knowledge initiative, and we will start grabbing the topics based on the arrangement order I received in WhatsApp group. I'll allow, if you have a slide or something, I'll allow you to share your screen. Sharing screen, you guys all check your Zoom black window. You will find at the bottom something called sharing screen. So I want to confirm, are you guys all having the same tab, sharing screen?
Okay, Doctor.
Okay.
It's okay for me.
Okay. Okay, my voice is clear for all of you?
Yes, it's clear.
Okay.
Yeah, it's clear.
Okay, so this is Mr. Salah. Okay. The first.
Yes, I am Salah. What's going on?
Okay, because the voice is a bit noisy. That's why I just want to make sure that you are either you are hearing me or you want to ask about something.
I hear you loud.
Okay, Mr. Salah. Mr. Salah, please check your internet connection because we cannot hear you clearly. Because if we reach to your topic, maybe we will suffer in hearing you.
I will log out and log in.
Yeah, okay. This will be okay. Okay, the first speaker already, Mr. Abbas Al-Khayyat. The topic is geosteering as geostopping. The stage is yours. You can share the screen.
And you can't imagine our life without.
Sorry? Okay, very nice. If you want to open your camera, it's okay. If you don't want, it's okay as well. This is up to you.
Hello, everyone. My name is Abbas Al-Khayyat. I am a junior drilling engineer with almost 2 years of experience working in the field. Thanks for Dr. Wael for this great opportunity to share knowledge with each other. Today's topic, my topic will be about geosteering as geostopping. This is actually a case study that was done in offshore of Australia with a gas reservoir. As you can see here, here is the outcrop of the reservoir. The top of the reservoir is actually shale, unreactive shale, and this is the pay zone that we are interested in. Now, if you can see here, the reservoir is actually highly permeable. So these formations are like 1.5 darcies, and this is like 8 darcies. So it can give us like, as you can see, a high flow rate. So considering all of these, this was the original well plan of the reservoir, entering the reservoir with a 12-quarter hole to maximize the production rate. But after after assuming so many scenarios, and it's an offshore well, not easy to drill, and considering kicks, blowouts, and all of these scenarios, the plan was changed in order to minimize the risk and keep the company's reputation. The company was Chevron. So they changed the plan into the final plan, which is stopping before the top of the reservoir, case the hole, cement the hole, then drill another section. So this is the final plan, and the plan was actually 3 meters above the pay zone, 3 meters vertically above the pay zone. And the unwanted scenario was entering the pay zone without knowing they entered the pay zone, which would lead into a disaster and change in the original plan that they wanted to do. So how did they achieve this? They used deep directional resistivity LWD tool. As you can see, here is the bit, the RSS, the LWD, and the MWDs, and the receivers. So what basically they did here is, when entering the reservoir, it was entering the reservoir into an inclination. So to using simple mathematics here, knowing the dimensions of the tool, they, as you can see here, here is the bit depth, and they were actually around 5 meters ahead of the bit. So they could tell, changing the resistivity from shale into the reservoir resistivity rock. Okay, they could tell that they are like 5 meters ahead of the bit, and they could tell that they are really near the reservoir and not to enter the reservoir. So as you can see here from the tool, okay, they could tell they are near the reservoir, and they could actually stop 3 meters above entering the top of the porosity. As you can see here, here is the change in resistivity entering from shale into reservoir rock, and this is the pay zone. They were able to stop here 3 meters above, case the hole, cement the hole, and run another section. Yes, it was a smaller hole that will give smaller flow rate, okay, depending on the completion they planned to. But as a conclusion, they were able to do it safely and keep the company's reputation. And they were not able to do it without using this method. That was their only solution that time, and to achieve this thing. So it's actually a case study published on SPE using geosteering as geostopping to stop above the reservoir.
1 minute. 1 minute left.
I think this is the final slide. Thank you very much, Doctor, for letting giving us this opportunity. If there's any questions, I kept it short as much as possible.
Okay. Yeah, this is nice. Thank you, Mr. Abbas.
Thank you very much. Thank you very much
for this good topic. Usually, we will get one question for each, only one question for each participant. So, you guys, if you have any question for Mr. Abbas Al-Fayyad. If anyone has a question for Abbas.
How is everything in Basra, Abbas?
Well, I live in the north. It's not in Basra. So Basra is hot, as you know. It's good. It's good. Operations are like low, but still surviving this pandemic.
Okay, that's good.
Okay, Saeed, do you have a question?
No, nothing, man.
Okay, for me, I have just one quick question. Do you have any other challenges more than the one that you are listed in? I just need just one more challenge, just another one challenge than geostopping.
Okay, this actually before starting, when they planned this one,
okay,
they said if there is any problem, we would need at least 2 relief wells in offshore.
Okay, that's great.
That was their biggest challenge. 2, at least 2, not even 1, at least 2. Based on this, as I said, this is, you see, highly permeable zones. So the flow rate, and based on the calculations they did for the kick scenarios, their flow rate would need at least 2 relief wells, and they would need to take platforms from other operators to drill these wells. And so it would be a disaster environmentally and for the company's reputation. That's why they changed their plan from this into this.
Okay, that's great, Abbas. Thank you for such a nice presentation and nice
Thank
topic.
you very much, Doctor.
Appreciate it.
Okay,
thank you.
Stop sharing.
Okay, stop sharing.
Thank you.
You're welcome. Okay. Our second speaker is Mr. Mohammed Anis, directional drilling, O2.
Autonomous directional drilling.
Autonomous, yeah, this is the first, for me, yeah. Autonomous directional drilling, yeah, okay. I thought it's autonomous director. Okay, autonomous directional drilling. Go ahead.
Give me just a few.
Okay, you have firstly to explain to us what is autonomous.
Yes, I will explain everything. Just
okay. Okay, go ahead.
But before to start, I want to inform you that I will take a little bit time. I think about 7 to 8 minutes. So if it's okay with you,
I'll give you 1 minute more and 6 minutes. Go ahead.
Okay, thank you. So the autonomous directional drilling, first of all, it's a competition. It's an international competition which is called Billbodex Project 2020, organized by the Drilling Systems Automation Technical Section, which is section in the Society of Petroleum Engineers. So Billbodex is a competition for universities to design and build a small drilling rig that uses sensors and control algorithms to autonomously drill a rock sample provided by the SATS. So first of all, we are a team from Algeria, from Qassim El Bahouregla University, and we are always working on this project. As you can see here, here's a picture of our model of our prototype.
Okay.
So last year, we participated in the vertical competition, vertical phase, which is the vertical drilling. So we got the second place worldwide and the first place in NAPEC, which is the North Africa Petroleum Exhibition and Conference. And here is a picture of our real device, our prototype. Our main sponsors were the Hassim Saud Professional Section from SPE, the FAST company, which is a Chinese company specialized in drill bits manufacturing, the Ali Hassim Saud, which is the training school in Algeria, and the main sponsor, the ENTP, which is a drilling national company in Algeria with more than 68 rigs, drilling rigs. So, okay. Wrong. I have problem with my laptop.
It's okay. In flipping the slides.
I have problem with I can go to the next slide. I don't know.
Okay, can you have mouse?
Sorry?
You have mouse? You have mouse?
No, I am using directly my laptop.
Okay, no, just be calm. Okay, because maybe you can stop sharing and share it again.
So it's okay. It's okay now.
Right click and go to the next slide.
It's okay now. It's okay now.
Okay.
So the final test is organized in the drilling simulator Cella in Germany with 16 universities from 12 countries across the university in Germany, and the presentation is organized always in the research center of Baker Hughes in Germany. So the autonomous directional drilling, so what is our main objective is to drill a deviated well in 3D plan, which means we have change in azimuth and inclination at the same time in order to hit multiple targets at different XY coordinates and vertical depth Z. As you can see here, we have a model of our rock sample. So after drilling the vertical phase here, we will go to the target A with X, A, Y, A, and Z, A. And then we will pass to, after drilling the target A, we pass to the target B. So as you can see here, we have a build. Then we have a drop with a small change in azimuth, as you can see. Okay. So in order to answer this phrase, we have to work on these 4 points. So first of all, we have to design and build autonomous miniature physical drilling rig, and this is the main objective. Design a flexible, controllable mechanism, especially for the BHA. Design a closed-loop control algorithm based on downhole data, real-time data, and finally create a human interface for data visualization and supervision. So maybe most of you will ask what is the difference between automated and autonomous, because maybe some of you heard about the last technology of Baker Hughes, which is the iTrack, the automated directional drilling. So the autonomous means acting alone or independently, which in this case, the device have the auto decision option. But the automated is just control and operate according to specific steps. And there is no auto decision in this case. And here is another example. For example, in the left here, we have autonomous car with auto decision. As you can see, the driver is enjoying his coffee while the car is driving alone. In the other side, we have an automated device. So in this case, the device always needs a human intervention to put the steps or the program. So our BHA and directional tools. So this is our own design. So from the top to the bottom, we use the sensor sub, which is the location of our downhole sensor. We used new tools. This is totally new tools. It's electrical knuckle joint with a downhole motor.
Two minutes.
BHA stabilizer.
2 minutes left.
Sorry?
2 minutes left.
Okay, and we use downhole air motor to ensure the rotation of our micro bit 1 inch. And for the data transmission, we use the wired drill pipe to ensure the data transmission. So there is the main components of our electrical knuckle joint. We have fixed upper part, mechanical brake here, and movable lower part to make the deviation or the inclination. And this is the canalization of our flow to rotate our drill bit. So we use this is a real picture of our downhole motor, and this is our control, the control of our downhole motor. Here we have a speed control with closed loop, and this is very important in auto decision device. This is a real picture, or not a real picture, it's a 3D model of our device from SolidWorks software. We use 2 sensors, main sensors. We use the load cell to measure the suspended weight in order to get the weight on bit value, and a downhole sensor composed of 3 sensors with gyroscope, accelerometer, and magnometer to calculate the inclination and the azimuth and the angular velocity. So to optimize the BUR, which is the build-up rate, so we use the PID controller. So it's based on downhole feedback from our downhole sensor, IMU. So we'll get the inclination alpha. Then this inclination will be filtered with Kalman filters. You can Google it if you want to know more how it works, the Kalman filter. After that, the Kalman filter will the filtered inclination will be transferred to our compensator to calculate the error or the difference between the first set point and the second value of our sensor.
1 minute left.
Okay, and then the PID controller will switch this inclination into RPM set point. So will give us a new output RPM. So in order to correct the inclination, we have the downhole motor have to turn, we have to get a new output RPM here. The same thing for the weight on bit control. So I don't have much time. There is an example. Is our general algorithm. So I can share more because it's a little bit confidential. And this is our scale control. We use 4 actuators with 4 servo drivers. Just for the air compressor motor, we use the VFD variable frequency drive. And in the other side, we have our 3 sensors, load cell, flow meter, and our downhole sensor. And all this device are controlled by MATLAB. And this is very, most of you know what is the MATLAB software. So in the conclusion, this technology will give us high performance with high precision thanks to the auto correction by using PID controllers. It's more safe thanks to our emergency response algorithm. We give our real-time data acquisition thanks to the welder pipe, optimum ROP, and good selection of the drilling parameters, and the mechanical specific energy, which is MSC optimization. And this device will also give us more flexibility and the ability of changing the well plan at any depth. And finally, less time, which means low cost. Thank you for your attention, and sorry for taking too much time. So for more details, you can follow me in my Facebook or LinkedIn account. And thank you, Dr. Wael, for giving us this opportunity and for organizing this amazing and interesting sessions. Thank you for it.
You are welcome. Thank you, Mohammed Anis, for this nice presentation and this nice project.
Thank you.
This is a very good job. Any question? Anyone has a question for Mr. Mohammed Anis?
Yes, I have one, Wael, please, if you allow me.
Okay, go ahead, Mr. Sulaiman.
Yeah, thank you, presenter. My question is how, I like the word autonomous. It's a political word, so I'm surprised how they use it in the drilling system. My question is how this autonomous device adjusts for the uncertainties in the rocks down there.
What do you mean by the rock?
When you are drilling, you have a plan, but
yeah.
and in the subsurface, you have uncertainties on the formation depth, on the thickness. So how the device, is there algorithm to adjust if you have surprises down there?
Actually, we have two optimization algorithms here. As you can see here, we have two blocks. These two blocks are very big algorithms. So if you enter in the inside, we'll find another algorithm for the vertical phase and for the directional phase. For example, for the vertical phase, the optimization algorithm will work to optimize all the drilling parameters. For example, if we have a change in the formation, so our device will optimize automatically the drilling parameters to ensure smooth ROP, good ROP, and to prevent, for example, or to minimize vibrations or any other issues related to drilling operation. And for the deviated case, so here we have to enter or to input our coordinates, our target coordinates. Then the system will follow and correct and correct all the parameters according to our coordinates. So if we have, yes.
Yeah. So this thing is for the tangent part of the hole, not for the horizontal drilling, is it?
Yeah, for the just for the deviated well, directional, not for the horizontal. The horizontal is another.
Thank you, Mr. Sulaiman, for the question, and thank you, Mohammed. We have quickly just answer this question. Which language you use? The question came from our colleague Amr Abdel Fattah. Which language has
we are using just, yes, we are using just MATLAB software by MATLAB.
Okay,
MATLAB
thank you. Is it how many times it was being tested in real time?
Actually, we just tested the vertical phase last year, and this year, unfortunately, due to coronavirus pandemic, it was planned to test the device in Germany in this June, and it was postponed until next year, inshallah.
Okay, thank you, Mohammed Anis. Thank you for such nice presentation. Wish you all the best. Our third speaker, Mr. Saeed Al-Qasabi. He will teach us about azimuthal measurement and geosignal. Starting from now, quickly, the speaker will introduce himself, and just his name and his job title. Maybe his job title only, if he didn't mention it in the presentation, or that's it. Okay, go ahead, Mr. Saeed.
Assalamu alaikum.
Alaikum salam.
Hello everyone. Actually, my name is Said Al-Qasavi. I have joined the Halliburton since 2009, so you can say I have 11 years experience in oil industry. I did several roles, started with mud logging and data engineer stuff, and then I transferred to MWD and I promoted to doing ROC roles, remote operations, and now I'm currently MWD coordinator for Geosteering. Before I start, actually, I cannot say it is like a session. It is just like some tips I try to emphasize after your introduction, Mr. Wael, about this geosteering. So I found myself I can add something regarding to this imaging and geosignal. So I'm just need to emphasize some stuff. Maybe the guys with no experience in LWD imaging and all this stuff, they don't know. So I tried to add something different. I was supposed to speak about MWD overview, but I found a lot of guys are interested, so I just got this part. So here I'm starting with the Azimuthal deep resistivity imaging, and I here actually I need to speak in this particular case for imaging capability. What is the tool needs to have the imaging capability? What does it mean binning? For the guys who doesn't know, the idea of imaging or binning is the capability of the tool to divide in the borehole into a definite number of divisions. Like we can say the borehole is 360 degree. So we can make like, depending on the tool capability, like we have in ADR, we have the capability to divide the borehole into 32 bins. And we have also other tools, we can make it like 128 bins and even more. And even Schlumberger, all the competitors, all the respective companies has some capabilities. So it's different from company to other company. So we call the tools which can bin or from which we can get image the smart sensor. So the tool should be smart. Why? Because to have like azimuthal binning, you can divide the tool. You have to make like high side, or you have to have reference from where you start binning, or from where you start your number one in bin, where you will find number one, when you will find your bin number two, when you will find bin number three, and so on. So here it is just a simple example. It's showing going through different formation, fluid bearing formations. One is oil and the other one is water. And here it is showing this difference between high resistivity and low resistivity and the binning idea. As I said before, the capability of any tool to be start.
2 minutes left.
Okay, to make binning, just first of all, I said you have to have the bin reference high side, so you have reference of your high side. Maybe it is high side of the hole, and maybe it is magnetic north. So you have, this is related to directional sensors. So you have to have RPM, and you have to have internal offset for this smart tool to this directional sensor. So once you got this good survey, or as we said, you know where exactly your high side of the hole, and you start binning the entire hole into the number of the bins, which is identified by the tool capability. And here for this is a simple example for this trajectory during geosteering. And here you can see the ability of going image. You have also the upside and downside from the hole. It's giving you an idea of the approaching the bit boundary. So in the left side, you can see the down measurement is different than the up measurement. You can see the up measurement is spiking up, reflecting the increasing of high resistivity approaching the low boundary. I guess I don't have more time, but I have to go to this
1 minute.
geosignal behavior. Okay, for geosignal behavior, the idea behind the geosignal, you will just take only one measurement and calculating this geosignal. So as we said, if we'll take the up geosignal, you will take the raw data from this up sector and minus the average of all sectors. So as example, if you can see the right image or left image, you can see here the sum of all the bends is 15 degree, and the upper one is 20. So you can have this geosignal measure. So if geosignal is above 0, it means that the formation of higher conductivity is above the sensor. If it is negative, the formation of higher conductivity is below the sensor. And this is a simple example of how it works. You can see in track 1, it's, we are going from the high resistivity formation to low resistivity formation. Track 2 is just the resistivity, which is conventional one, which is the average from all pins. Track 3 is just,
this is last slide.
Yeah.
Okay.
The track 3, it is geosignal, and what I need to emphasize here, you can see the blue curve is the up geosignal, and the brown one is low, and it is spiking up, reflecting the change in resistivity measurement. And track 4 is the same, but it is for resistivity, not for geosignal. And you can see here we are spiking toward the high resistivity formation. So you can see here we are spiking the bottom trace of resistivity, which is spiking, not the upper one. So maybe it is vice versa of geosignal. I wish you got my point. That's it.
Thank you, Mr. Said, for such detailed and to the point presentation. Actually, we have anyone has a question? Okay, so we have a question from Mr. Rami Abdelghani. Could we consider this tool to be imaging while drilling, like FMI for sedimentary structures?
So imaging, yes.
I mean, maybe Rami is asking, can we get like such nice sedimentary structure or fine detailed sedimentary structure like we are getting from wireline resistivity tools? Maybe this is a question.
Yeah, for sure, we have the tool has this capability to have, as I said, you have different output of the tool. At the top of track 5, you can see the image, and going down, you have the azimuthal reading. You can have the top quad, bottom quad, left, right, even the bends, and also you have this geosignal, which is single measurement. So you have a lot of output. One of them for sure is the image, and this is imaging tool. So this is one of the tool capabilities.
Okay, thank you, Mr. Said, for your presentation. Now we'll move to our coordinator for this course, my active student, Ahmed Abdelrazik. He will speak about why we do geosteering. Said, you can now stop sharing. From, yes, okay.
Okay, thanks for this intro, my doctor. Are you hearing me? Are you hearing me?
Yeah, we are hearing you very clear.
Okay, first I thank you for this opportunity and Ruji company for this chance. Actually, it's an easy topic relative to other topics of the day, but it's very important to know why we use geosteering. Geosteering may be used to keep well bore in a particular section of a reservoir to minimize gas or water breakthrough and maximize economic production from the well. but this is the definition. But what I understood yesterday from Dr. Wael is to land the well in optimum target zone and to maintain the well bore in the zone of maximum interest, predicting and proactively avoiding, of course, reservoir exit. And also to minimize gas or water breakthrough and maximize economic production from the well. Then the benefits of geosteering: increased production, reduced not production time, quicker decisions, real-time data aggregation and visualization, ultimate recovery. I think each point will be presented today by other presentations. Avoiding sidetracks, faster drilling in target zone, reduced drilling time, smooth well pour, and of course reduced well cost. My presentation is very short, but the topic is very simple. Yani. Thanks, Doctor. Any question?
Thank you, Mr. Ahmed.
الله ينور ابو حميد.
يا دكتور بنورك.
Okay, thank you, Ahmed. We will move to our fifth speaker, Mr. Mustafa Atiyah. He will teach us about elevation reference. The stage is yours, Mr. Mustafa. Mustafa Atiyah, are you hearing me? You guys are hearing me? It's okay? Any issue with the sound?
Okay. Yes, okay, it's clear.
Okay, so now maybe. Okay, Mr. Salah, Mr. Salah Ad-Din, just wait. Okay, now we will skip Mustafa till he will be ready. We will go to the sixth speaker, number 6, Mr. Jerome Sevier. He will talk about MWD. The stage is yours.
Hello, Wael, do you hear me?
This is Mustafa Atiyah?
Yes, sir.
Okay, excuse us, Jerome. We will pick Mustafa. Mustafa, go ahead.
Okay, just let me share this.
Okay, go ahead.
Is it coming up on screen?
Yeah, this is okay.
Okay, hello everyone. This is Mustafa Atiyah. I'm from Egypt. I have been working in the oil field for more than 10 years now.
Sorry, my mic wasn't working fine.
Okay, who's this?
Jerome.
Okay, you will come directly after this.
Yes.
So just hold on.
Yes.
Okay.
So this is Mustafa Atiyah. As I said, I've been working in the oil field for more than 10 years right now. I'm working with Halliburton as a data engineer and a well site geologist. Today, my topic will be very short, just to maintain the time. I'm going to talk about the elevation reference and some definitions. For sure, in the drilling, we need to refer to any optimum reference. So RKB is rotary table is our main reference. I'm going to talk about some definitions today. The measured depths, which is the total length of the well bore measured along the actual well path. As in this figure, this is showing the measured depths, and the TVD is the vertical depths of the well bore independent of its path. So we measure the TVD vertically from the surface down to the a certain target down the hole, and it's derived from an equation which the TBD equals the MD multiplied by the cosine the inclination. And the one who's usually responsible for providing us this is the directional driller. The other thing which could be unknown for some of us is the true vertical thickness, which is the thickness of the rock layer measured in a vertical well bore. Usually we will deal with this in the geosteering, as we need to define the layer, each layer. So if we need to steer in this layer, we should know the thickness. The other thing is the true stratigraphic thickness, which is the thickness of the layer measured perpendicular to the layer. And we can, in the conventional geosteering, which we don't have any Azimuthal tools, we cannot calculate this one. So we'll be using the one of the offset wells. But to calculate this one, we need to know the depth, which recently the Azimuthal tools provide us this the formation depth, so we can calculate the true bit thickness. I'm not gonna add much. Thank you for your time, and thanks Wael for this opportunity to speak to such nice guys. Thank you very much.
Okay, you are welcome. Thank you, Mustafa Atiyah, for such quick and to the point knowledge. You guys have any question for Mr. Mustafa? Okay, thank you, Mustafa, for such a nice presentation. We will move to Jorim Xavier, MWD. I will talk about MWD. Go ahead.
Hello.
Hello.
Yes, this is Jerome.
Okay.
Should I start now?
Yeah, you have something to share, or you just speak?
No, of course, I will share my screen right now.
Okay, share. Okay, go ahead.
Okay, so can you see my screen?
Okay, if anybody want to open his camera during his presentation, this is optional. It's okay. He can do it, or this is as per him.
Okay, is my screen visible for everyone?
Yeah, visible.
Okay, so hello, my name is Jerome Xavier. I'm a petroleum engineer. I'll be enrolling at Texas A&M University next fall for my master's. I'm going to be talking today about drilling and geosteering. Okay. So first of all, MWD is the evaluation of physical properties, including pressure, temperature, and wellbore trajectory in 3D space while expanding a wellbore. The measurements are made downhole, stored in state memory, some state, and later transmitted to the surface. We can acquire our data. Data transmission methods vary from company to company. Usually it is digitally encoding data and transmitting to the surface as pressure pulses in the mud system. MW is a geosteering measurement without using these helps on changing our wellbore path depending on the scenario, whether we have a sudden fault, structural phenomenon, some pressure, unexpected kicks, or any structural geological phenomenon that Mr. Wael mentioned yesterday. The measured data are stored in MWD and NWD tools, and some of the results can be transmitted digitally to the surface, as mentioned using mud pulse telemetry. MWD tools are part of the bottom hole assembly, the BHA. They are located just above the drill bit, so we can acquire our data. The data is acquired from the drilling grid sensors for a range of purposes, such as it can help us do a decision. It supports the decision to monitor and manage the smooth operation of drilling, make detailed records or well log of the geologic formation. This is more into LWD. generate operation statistics and performance benchmarks such that the improvement can be identified, such that the ROP, rate of penetrations, and the WOB, weight on bit. Provide well planners with accurate historical operations performance data.
2 minutes left.
Perform statistical. Yes, I'm done.
Okay.
I'm done. This is my last slide.
Okay.
The borehole is drilled according to the well plan. New geological is gathered from mud logging, measurement while drilling, and logging while drilling. These really show some differences from what is expected from the model. MWD is used for well path coordinates for successful geosteering. These are some pillars of the MWD systems. This is the 3D coordinate system. And this is also another system for the bottom hole assembly showing the MWD, which will measure all the mechanical parameters that we need for our drilling operation and unexpected drilling events. Thank you for attention. Sorry if I took more than 2 minutes.
Okay, no, thank you, Jerome, for such review for the MWD system. Actually, this one we passed yesterday. We just get a quick review in MWD, so this is a good emphasizing for MWD system. Any question for him? Okay, we will. Thank you, Jerome. The stage now.
Thank you very much.
You are welcome. Will be for Geosteering Iki. He will speak about real-time transmission.
Assalamualaikum warahmatullahi wabarakatuh. My voice is clear?
Yeah, your voice is nice.
Okay. My name is Yustian. I'm on site real-time support for petroling. Daily I support Geosteering Operations Center in Saudi Aramco. And I will explain about real-time data transmission and visualization for drilling and geosteering project. So to understand about the real-time data transmission and visualization, I will explain about real-time data infrastructure here. It will start from the aggregation. So once the data come from the tools, it will come as a WITS, well site information transfer standard, or directly come to the machine in the rig as a WITS-ML or well site information transfer standard markup language, which I will explain later. What are the difference? The standard here is WITS-ML. So if the data come as a WITS, we have to convert it on WITS-ML and on the special application on the rig side. So once it's translated to WITS-ML, the data will be transmitted to the very small aperture terminal or VSAT on the corporate server in the town. During the transmission, the satellite node will be divided to several nodes. So, this is kind of a backup program in case the network is getting very weak or getting weak. So two or one of the node, in case one or another node is not functioning well, the other node will be able to transmit the data to the phone. And then once the data comes to the corporate server in the town, it will be connected on the console, which is like a canvas to display whatever comes from the rig, like LWD parameter or any drilling parameter, and that will be ready to be analyzed by the geologist or the drilling specialist. And this is the difference between the WITS and WITS-ML. Why we have to convert the data format to WITS-ML? Because this is relatively lighter and it mentioned the parameter clearly.
2 minutes left.
Meanwhile, in the WITS, Sometimes the rig convert switch the channel with the different channel. You can see here 0208 translates as the MD or the big depth, something like that, and so on. And meanwhile, in the WITSML, it mentioned in the each strata here, and reading will come later, and this will be a lighter format. And once it comes to the corporate server, it will be used together with the static data reference, like drilling plan, offset, well data, information grids, to decide and to be analyzed by the geologists, and the geologists will be able to decide how much the inclination needed to adjust the drill bit to get more contact with the reservoir. And I will be more than happy if you have any questions. Thank you.
Thank you, Justian, for such a nice talk, especially for me, because I was working with you guys in Saudi Aramco. Petrolink was the coordinator for the data transmission. Now I know the cooking secret for behind the Petrolink. Thank you for such a presentation. You guys have any question for Mr. Justian? Okay, we will move to our brother Muhammad Yunus. He will speak about real-time, the difference between real-time and recorded mode data, LWD data. Okay, go ahead.
Hello, good evening, Wael. This is Muhammad Yunus.
Yeah, good evening, Muhammad.
And so, is it possible to basically, it's a very straightforward one-page.
Okay, now I'll. You asked me to. No, okay. Go ahead.
If it is possible, it's okay. Otherwise, it's very straightforward. I can
okay.
speak on mic, right?
No issue.
Okay. My topic. First of all, thank you very much for giving me this opportunity to speak. And I hope when I am speaking to all you guys, all the guys are in the best of their health and be happy during this pandemic. So I wish you all the best of luck. So real-time and recorded mode data. A real-time data means receiving the data at the surface during the drilling operations. So this is real-time data is the fresh data. So it minimizes the time delay. It is the data from uninvaded zone. It is closer to the true formation. As you know that wireline data obtained after drilling before fluid invade deeply. So the quality of data may not be good. Normally it's good, but if in case it is not good, it is actually the representative data. So the real-time data we received at the surface during the operations. On the other side, there is a recorded mode data, and a recorded mode data is recorded.
I'm helping you, my brother. Yeah. Okay.
Okay, it's okay, no problem.
Okay, you guys can see this. He already sent it to WhatsApp group.
Yes. So the recorded data, it's being recorded in the memory tool downhole. As the drilling progresses, the LWD part of that BHA will record the data, and that recorder will be downloaded at the surface. So the recorded mode data contains all those formation evaluation parameters, resistivity, gamma ray, porosity, like neutron, and other relative formation evaluation data. So MWD is the real-time data which we received at the surface. So it is being communicated through the mud pulsar. So it has azimuth, inclination, and the 10% of the data which is being borrowed from LWD to MWD. So this is 10% data. Yeah, this MWD acquire 10% data from LWD tool, and it is internally connected through the extender. So what we get at the surface, at the surface in the truck, it's LW data along with the MW data, but it is not complete data.
2 minutes
only
left.
10% of the, yeah, it is only 10% of the data. So we will get LW data at the surface. So because LWD has no ability to transfer the data from BHA to the surface. So we get the support of MWD to transfer 10% data. So then the data processing at the field, the data which we have received at the field, we at the truck, we can prepare the rush print like MW data and LW data, and with the some few channels which we received through MWD, we can make use of those for our information transfer.
1 minute left, my brother.
And the rest of the done, yeah, the data processing, the complete answer product will be transferred to a data center at the Geoframe, Maxwell, Ideal to complete, to prepare the final answer product for the client. That's it. Thank you very much. If you have any question, you are welcome. I'm here to reply.
Thank you.
Thank you very much.
Thank you, Mr. Muhammad Yunus, for such a summarized knowledge about real-time and recorded mode data, MWD, LWD data. You guys have any question for Muhammad? Okay, thank you, Muhammad. We will move to the next speaker, which is Manar Sameh. She will talk about drilling risks. Manar, the stage is yours. Go ahead.
Good evening. My name is Manar Sameh. I am a senior student at the Geology Department at Alexandria University, and I will talk about the drilling risk. The risk with offshore and land-based drilling can be discussed in terms of unexpected events.
Manar, just a second. Make sure that you don't have any noise surrounding you, and please maximize, make the presentation in the slide mode, in the presentation mode.
Okay.
Okay.
It's good?
Yeah, this is good now.
Okay. Good evening. My name is Manar Sameh. I am student at Petroleum Geology Department, Alexandria University, and now we will talk about the drilling risk. The risk with offshore and land-based drilling can be discussed in terms of unexpected events associated with geological heterogeneity and complexity in the subsurface. And now we will talk about some of them.
loose rotation is the first. The uncontrolled flow of mud fluid from borehole to the formation is a result from underbalanced condition at which the formation pressure is larger than acidic pressure. And according to its severity, we can classify these losses to 3 types. Number 1 is seepage, when mud is lost into formation at very small rate, less than 20 barrel per hour. And partial loss return, when mud continues to flow to the surface with small losses to formation, greater than 20 barrel per hour. And total loss return, when all mud flow into the formation and no fluid come out to the annulus. Number 2 is draining kick. In the simple term, a kick is caused when the step pressure is not enough to contain the formation pressure. So the flow of formation pressure into the well pore will result. And the formation must be permeable to allow the fluid flow. And kicks can be caused by many scenarios, but in every possible situation, it will be caused by reduction in the step pressure and increase in the formation pressure. There are two types of kicks. Number 1 is underbalanced kick. Underbalanced kick, or when the formation pressure rises above the step pressure, while the correct mud weight has been maintained. Number 2 is induced kick. Induced kick are accounted when the step pressure drops below the formation pressure, and normally caused by lowering of mud weight. The step pressure may be dropped for many scenarios, but it is commonly caused by swapping to the hole with tripping or drilling to quickly through gas-bearing formation or making additions to mud system that allows the drilling the mud density. Number 3 is formation damage.
Manar,
damage to the formation will occur when
you have 2 minutes left. You have 2 minutes left.
Okay. And can cause the formation washout or borehole corrosive or reservoir flashing on contained between the fluids. This impact makes the drilling operation exposed to reduction in quality of borehole, which can lead in stability problems and damage or reservoir formation, or may reduce the final production capacity, and also can lead to the reduction in accuracy of wireline data. Number 5, the pressure caving. Pressure caving occurs when two conditions are met. The formation has no or very low permeability, or the pressure is higher than the mud pressure. And the pressure differential exists between the and if the stress is greater enough, it causes the formation to crack or calve stress. Typically, the caving are curved with a smooth concave side or trough convex side. But the pressure caving can be all or shapes or size depend on the source formation characteristics. And drill pipe failure can be the twist off. The result from failure in equipment like jar or mud motor, or from washout of hole or drain faults by making the weight on bit equal the weight below jar at long time. And finally, the pipe stack. We have to type of pipe stack like differential stack that occur between the mud column pressure and formation pressure. And it's a filter cake build up to isolation. The pipe can occur against the lower pressure formation.
Thank you, Manar, for such clustered information about drilling risks. Any question for Manar?